In this chapter, we're going to look at carboxylic acids and derivatives of the carboxyl group. Now, we've seen carboxylic acids already quite a bit. It's a pretty common functional group. We've seen it way back early last semester when we talked about just acidity and basicity in general. And we've seen it even back in the chapter on alcohols. And we saw that this carboxylic acids are kind of the final oxidative step of a primary alcohol group. And of course, we've continued to see it even in the last chapter on aldehydes and ketones. All right, so carboxylic acids are very useful, very versatile functional group, right? We've seen them already quite a bit in a lot of the reactions we've seen in lab. And as a result, you can imagine it's probably pretty useful from a synthetic chemistry standpoint. All right, let's start off with nomenclature. And like aldehydes, your carboxylic acids have to be a terminal group. So since they are usually the primary group, the highest priority group, I should say, they're by default put at the number 1 position, and we number the rest of the parent chain accordingly. Now, the suffix we're going to use to designate a carboxylic acid is oic acid. So just like with aldehydes, where you take the name of your alkane name of your parent chain and you swap out the E for the suffix al for aldehyde, here we're going to swap out the E for oic acid. All right, so if you have a 4-carbon chain, that would be butane as an alkane. So we swap out that E and it becomes butanoic acid. Okay, if you have 5 carbons, that would be pentane. So instead we change that to pentanoic acid. All right, now you can see an example here on the right. We can see where the locants are numbered, right? Since even though we have more substituents on the left of the molecule, we still have to number from the right because that's where our carboxylic acid is. Okay, so even though you could get lower numbered locants by starting on the left, it's 5-hydroxy 4,4-dimethyl pentanoic acid. Now, if your carboxylic acid is attached to a ring, of course, you can't really count the ring as part of the carbon chain, as part of as part of the parent chain with the carboxylic acid in that parent chain. So you actually have to take the sort of the alkane name of your ring and add the suffix carboxylic acid to it to show that the carboxylic acid group is kind of a substituent on the ring, but still the primary group. It's kind of weird, but basically here in this example we have cyclohexane. All right, so that's our alkyl group. But again, that ring, we can't count this as this carbon as part of that cyclohexane, right? So we can't call this cyclohexanoic acid. That wouldn't make sense, right? That in order for that to work, this carbon would have to be part of the ring. So instead we call it cyclohexane carboxylic acid to show that the carboxylic acid group is kind of attached to the ring. That being said, we have you'll probably also see an example like this in the case of benzene. Again, your carboxylic acid carbon is actually at the benzylic position, not part of the benzene ring itself. Now, that being said, instead of saying benzene carboxylic acid, the common name here is benzoic acid. All right, you've probably already seen benzoic acid in lab, and so you're familiar with that. A lot of some of the smaller acids have common names, just because before IUPAC laid down the rules for naming a lot of these compounds, people had names for these simpler carboxylic acids. So it might be useful to be familiar with them. Again, keep in mind they're not the IUPAC name, so please make that distinction. But just be ready to recognize them. Formic acid is methanoic acid in IUPAC nomenclature. If that sounds familiar, that's basically fire ant venom. All right, so the formic there being derived from the Latin word for ant. Over here we have acetic acid, all right, which also known as ethanoic acid to use the IUPAC name. Of course, that's a really common acid. That's the active ingredient in vinegar. We've probably used this in a few times in lab. So again, you've probably seen it labeled as acetic acid or seen its anion form acetate. Just realize it's the same thing as ethanoic acid or ethanoate if you're using IUPAC nomenclature. All right, propanoic acid is called propionic acid in terms of its common name. Not much of a change there, so most people I know just call it propanoic acid. Propionic acid's a little bit dated there, but again, you'll sometimes see that pop up, so be ready to recognize that. And butyric acid is the same thing as butanoic acid. All right, so butyric acid is the common name there. All right, now we've seen examples where there is, of molecules that have one carboxylic acid group at that terminal carbon. However, you could have more than one terminal carbon. In fact, you often do. And so it's possible, for example, to have a dicarboxylic acid or, ending with the suffix dioic acid. All right, so you're just adding sort of a prefix to the suffix there of di, telling you that there's two carboxylic acids on this molecule. Okay, now in this case, you don't really drop the E. You instead of, I think having two constants next to each other would be kind of weird. So, so basically, you leave the E in there, and it becomes, so we have 5 carbons here, counting those carbonyl carbons, and this becomes pentane dioic acid. Okay. Again, just like with our regular, monocarboxylic acids, we have a lot of common names here. So, ethane dioic acid is also known as oxalic acid. If we increase that by 1 carbon, we have malonic acid, then succinic acid, and finally glutaric acid. Okay, so glutaric acid and pentane dioic acid are the same thing, right? So keep that in mind in case you'll probably come across a few of these common names, especially like malonic acid or its anion malonate. Likewise, oxalic acid and oxalate are very common, so keep an eye out for those. All right, so let's look at some chemical and physical properties of carboxylic acids. Like our aldehydes and ketones, we have an sp2 hybridized carbon at the center of this functional group, which makes our carboxylic acid or carboxylate group flat. It's trigonal planar, right? So again, we're going to see that opens up that carbonyl carbon to a lot of similar reactions that we've seen in the last chapter. Another interesting thing here about carboxylic acid groups is that you can actually have them dimerize. So they kind of pair up, and you have the proton of one attracted to the carbonyl oxygen of the other. Okay, we actually saw this back in the chapter on IR spectroscopy. If you recall, this is the reason why the OH peak for your carboxylic acid is so broad. Right, this dimerizing effect really increases, that influence of that hydrogen bonding, and so instead of getting a merely broad peak like you would see for an OH group, you get a peak that's so broad it takes up like a third of the spectrum. So something to keep in mind there in terms of something that carboxylic acids are capable of. Okay, in terms of like physical properties, this is why. Carboxylic acids have relatively high boiling points compared to, similarly sized molecules. Okay, so for example, if you compare acetic acid to, isopropanol, right? In the example we've got here, notice that we've got a significant change there, like almost 40 degrees between those two boiling points. All right, you've probably heard me. Refer to the anion forms of these carboxylic acids. So we call those carboxylates. Okay, so a carboxylate ion is when you deprotonate the acidic hydrogen, the acidic proton on your carboxylic acid group. Now, to name these carboxylate ions, you just take that ic acid ending and replace it with ate. All right, so in other words, basically your anion has the suffix -ate, just as your acid has the suffix oic acid. All right, so you're probably familiar with a lot of these. I think I've already referred to ethanoate or acetate. It's a pretty common anion you see from a carboxylic acid. Another one you've probably seen is benzoate. Sodium benzoate is potassium benzoate. Those are very common preservatives. So you've probably seen them on ingredient lists on food items. Okay, so so again, these are pretty easy, relatively easy to make to turn into salts. These carboxylic acid groups are relatively acidic. At least compared to most organic compounds. They're not as acidic as, let's say, hydrochloric acid or sulfuric acid. But again, if you have a strong enough base, and sodium hydroxide, potassium hydroxide, those are definitely like strong enough to do it. Those will deprotonate them easily and give you the resulting carboxylate salt. Okay, so let's talk a little bit about that acidity. Again, this should ring a bell from some of the topics some of the examples we've looked at way back in chapter 3 when we talked about acidity in general. So we just saw that a metal hydroxide is a strong enough base to deprotonate a carboxylic acid, and that makes sense because if we compare the pKa of a carboxylic acid, which is somewhere in that 4 to 5 range, with that of water, which is the conjugate, the conjugate acid of hydroxide, that the pKa of water is somewhere around 15, right? So it makes sense that if you have, a protonated carboxylic acid and water on the opposite sides of equilibrium, the equilibrium will shift towards the water side. In other words, hydroxide is strong enough to deprotonate an acid because a carboxylic acid is a stronger acid compared to water in that reverse reaction. Okay. Now that being said, though, in the absence of hydroxide, if you just have water present, as we have over here, the thing to remember, though, is that in the grand scheme of things, we still treat a carboxylic acid as a weak acid, overall. Okay. That being said, again, remember, acidity is relative, so you've got to keep in mind what else is in solution. Okay, but to make sense of this from a numerical standpoint, like I said, keep in mind that your pKa values for carboxylic acids tend to be in that between 4 and 5. Okay, and of course, like I think I mentioned earlier, if you want to compare to to inorganic acids like hydrochloric acid, sulfuric acid, those are really acidic, right? We're talking about like -7, -9 in the case of sulfuric acid, way more acidic, but as I mentioned earlier, acidity is relative, right? If you compare carboxylic acids to other organic molecules, like let's say, like an alcohol is somewhere in that 14, 15, 16 range, clearly carboxylic acids are way more acidic than those types of molecules. Okay, so again, you can trace this back to concepts we learned way back in chapter 3. Think about REO. Think about how the negative charge on your oxygen is stabilized through resonance. With that carbonyl group. So if you deprotonate this oxygen, that negative charge on here will be spread to the other oxygen because you can have those electrons go here, and these electrons in these pi bonds move to this oxygen, giving it the negative formal charge. So that's basically what stabilizes that conjugate base. Okay, if because of this sort of in-between nature of carboxylic acids, they have carboxylates, their conjugate base, which are decent bases. Again, not to say it's a strong base, if you want to use the overall term, but acidity and basicity is relative. So it's actually quite easy to make buffered solutions using carboxylic acids and their salts, carboxylates. Okay, so that being said, if you ever have to calculate the pH of a buffered solution, you can do it quickly and easily using the Henderson-Hasselbalch equation. This is something you probably covered in Gen Chem. You can just plug the numbers into here. This is just essentially taking the sort of the negative log of your Ka expression for the equilibrium of a weak acid and its conjugate base. Okay, but you could just plug in the numbers into here. So if you take the pK of your acid, take the concentrations of your carboxylate salt and the carboxylic acid, and take the log of that ratio, that should give you the pH of your buffered solution. All right. Again, you probably won't see too many problems like this. This is more of a Gen Chem problem, but for what it's worth, you can still apply this concept from Gen Chem to these systems. Okay. I mentioned that we see a lot of these carboxylic acid functional groups are pretty common. That includes in biochemical systems. We see pyruvic acid is probably a good example. Succinic acid that I mentioned earlier, that's glutaric acid. Those are all kind of common molecules you'll see in biochemical pathways, right? So so basically you based on the pKa we're dealing with here, often under physiological conditions, you typically wind up having the carboxylic acid deprotonated at that pH. So it actually exists as the conjugate base, as the carboxylate salt. Okay. Other effects affecting pKa. Again, this is all like kind of hopefully a little bit of review from chapter 3. But keep in mind that you want to stabilize and delocalize that negative charge from your conjugate base. One way to do that is through induction. That's the I in ario. And so if you have electron withdrawing substituents, that tends to lower your pKa. It makes your carboxylate more stable and therefore makes your acid more acidic. So you can see here as we add more chlorines, which are very electronegative elements, our pKa drops further and further. Likewise, the closer that chlorine is, the lower the pKa. As we move the chlorine further and further away, notice that the pKa goes up. Okay. This also applies to benzoic acids. Having an electron withdrawing group on your benzoic acid again helps in much the same way and lowers your pKa. Likewise, the opposite effect can be observed when you have an electron donating group. So notice that going back to a couple of chapters ago when we looked at electron withdrawing, electron donating groups, or activating, deactivating groups on our benzene ring. So if you have a strongly deactivating group like a nitro group, notice how low the pKa drops, as opposed to a strongly donating group like this alcohol group here, which completely raises the pH to about, the pKa to about 1 unit more than that of the nitro version. Right, actually over, like it's a 1.1 difference there. Okay, so again, remember this is on a logarithmic scale. So this is with this substituent, the nitro benzoic acid is 10 times more is over 10 times more acidic than the alcohol derived version. Okay, so let's talk a little bit about preparation of carboxylic acids. We've seen a lot of synthetic methods already over the last few chapters to make carboxylic acids, going back to last semester. So remember back to the chapter on alkynes. Last semester we saw that you can do an ozone cleavage, and basically with alkenes, when you use ozone to cleave them, to do ozonolysis, you'll get two carbonyl compounds. In the case of an alkyne, instead of getting just a plain carbonyl, you wind up getting the corresponding carboxylic acids. Okay, so something to keep in mind. You're basically splitting along that triple bond, and both of those carbons go on to be the carboxylate group that we see, or carboxylic acid group that we see. Okay, we saw in the chapter on alcohols that we can oxidize oxidize primary alcohols all the way to a carboxylic acid. If you use a strong enough oxidizing agent, it won't stop at the aldehyde. You typically have to use PCC, or pyridinium chlorochromate, to stop at that aldehyde level. So most your typical strong oxidizing agents like sodium dichromate, chromic acid, potassium permanganate. All of those will take your primary alcohol and just oxidize them all the way to a carboxylic acid. All right. We've also seen that these strong oxidizing agents will oxidize the benzylic position of aromatic compounds. So if you have some, functional group, some alkyl group, for example, coming off of your benzene, that carbon that's one removed from your benzene ring is very prone to reactions. It's kind of allelic, essentially. And so what happens is we oxidize there to make the corresponding benzoic acid. Okay, so that being said, let's look at some new ways to make carboxylic acids. If you have a nitrile group, so that's a carbon triple bonded to a nitrogen, that can be hydrolyzed to a carboxylic acid. So just using an acid and heating it up will turn that into the corresponding carboxylic acid. Okay, so basically, we can add a nitrile group relatively easily. We've seen that already, in previous chapters. Cyanide, the cyanide ion is a pretty strong nucleophile, so we can tack that on to any R group using some substitution reaction, right? Especially an SN2 mechanism here using this primary alkyl halide. And then, of course, like I said, you can just hydrolyze that using an acid and heat and turn that into the corresponding carboxylic acid. The other method that we've seen, we may not have seen this example specifically, but we have seen Grignard reagents acting as carbanion nucleophiles on carbonyl compounds and converting them to the corresponding alcohols. Well, if you use carbon dioxide as your electrophile, what happens is that instead of having an R group and an alcohol, you wind up having a carbonyl on your resulting product, and that quote-unquote alcohol group is just the OH part of your carboxylic acid. Okay, so that's actually what happens if you use carbon dioxide. This is typically used in the form of dry ice, by the way. We don't use gaseous carbon dioxide for this. It's typically you'll throw in chunks of dry ice into your sample of your Grignard reagent in ether. Okay, and that's typically what produces this resulting product. Okay. Oh, just as a reminder, you technically get the carboxylate ion when you do the reaction. You don't get the protonated version directly. You have to add a proton source in a subsequent step to get the resulting protonated product. We kind of covered this in previous chapters, but you do not want to add your proton source into the same reaction with the Grignard reagent. You don't want to mix these two together because then your Grignard reagent just takes a proton from here and leaves as the resulting alkane, and you've wasted your Grignard reagent. So yeah, you want to add your proton source after the you've given your Grignard a chance to react with the dry ice. Okay, so here's an example of that reaction. So here we have phenyl bromide. You can convert in the corresponding Grignard reagent, reacting with magnesium and ether, just reflux it together. You'll make the resulting Grignard reagent. Now that carbon's nucleophilic, so if you have it react with carbon dioxide in the form of dry ice, it'll make the resulting carboxylate, and then in a subsequent step, add a weak acid, and it'll make the corresponding carboxylic acid. So that's how we make carboxylic acids. Let's look at how we can use carboxylic acids as a reactant. So what kind of reactions can we do with carboxylic acids as our substrate? So we looked at oxidations to carboxylic acids. Let's look at reductions of carboxylic acids back down. We've seen before that lithium aluminum hydride is a very strong reducing agent. It will convert your carboxylic acid back into a primary alcohol, and it'll go through that aldehyde intermediate. Okay, so we've already seen that lithium aluminum hydride will reduce aldehydes down to primary alcohols and ketones, of course, into secondary alcohols. But in this case, if you have a carboxylic acid, it will reduce it all the way back to a primary alcohol, okay, via that aldehyde intermediate. So basically the mechanism, works where you deprotonate. You start off with your lithium aluminum hydride acting as a base. It deprotonates your carboxylic acid, makes the corresponding lithium carboxylate salt. Okay, so you have this stable carboxylate ion. Okay, now this coordinates to your aluminium, right, in your aluminum hydride center, and basically it sends one of the oxygens to your aluminium. All right, so you basically have these electrons swinging down from that negatively charged ion, and it reforms the carbonyl and gives you the aldehyde accordingly. All right. Now, of course, then you can have that aldehyde reduced in the same way we saw in the last chapter. All right. So your hydride, of course, is a nucleophile. It'll attack that carbonyl and swing those electrons up to that oxygen, which can then be protonated to give you the resulting alcohol. So we see that step here. Basically, we can, you have your hydride ion effectively is a really strong nucleophile, attacks that carbonyl, shown here as it's attached to that aluminium complex. So basically, you can think of those electrons from that bond going to the carbonyl, swinging those electrons up, and so you start off with this or you wind up with this ion, which you can then protonate to give you the resulting primary alcohol. Okay, so now that being said, another way to do the reduction is to use a mild borane agent that's also capable of reducing your primary your carboxylic acid down to the primary alcohol. So using a borane complex with THF or tetrahydrofuran, that'll also get the job done. Okay. Now, the nice thing about your mild borane agent is that it's mild. It will selectively reduce your carboxylic acid, but not reduce other carbonyl compounds. So, for example, here in this molecule, we have a carboxylic acid and a ketone. Notice that when we use our borane, we get the resulting ketone that stays intact, but our carboxylic acid winds up down at as a primary alcohol. Whereas if we use lithium aluminum hydride to do this, we would wind up with a secondary alcohol over here where the ketone is. Now, we've talked about a few reducing agents. You're probably saying to yourself, like, wait a minute, why, you mentioned sodium borohydride as a reducing agent in the last chapter. Why aren't you using it here? Sodium borohydride itself is kind of selective as well. This gets kind of confusing for students. It gets confusing for me, and and I've obviously known about this stuff for a while. Some of my former students asked me to make this slide where basically I've kind of summarized all of the different reducing agents that we've seen and that you'll come across. And you can see here what they react with and what they reduce your substrates into. Okay, so it might be useful to have this slide open when you're trying some of these reduction problems, or just in general when preparing for a quiz or exam. Just make a flashcard with this and try and remember which reducing agents reduce which reactants and what they reduce them to. Okay, so like I said, I didn't mention sodium borohydride because notice that it only reduces ketones and aldehydes. It does not reduce carboxylic acids. Okay, likewise, I mentioned earlier, like borane is also kind of selective. Just for carboxylic acids, it doesn't reduce aldehydes or ketones. Okay, so this is a good way to differentiate things. But if you have a reactant where you want to get multiple groups down to the resulting alcohol, something stronger like lithium aluminum hydride might not be a bad way to go. Okay. Of course, there's some things in here that some reactions we haven't seen yet. Like here, we can see we talk about amides and nitriles. Some of that will come up a little bit later on. Amides are another acid derivative we'll talk about later on in this chapter. We'll be able to talk about acid chlorides, acid anhydrides later on as well. So we'll get to that soon. Okay, so again, you might want to refer to this slide later on. Oh yeah, and esters as well, of course. Okay, so with that in mind, that's probably a nice segue into carboxylic acid derivatives. Let's talk about acid chlorides and amides and esters and whatnot. Okay, so if we look at oxidation states, so this is going back to a topic that came up way back when we talked about alcohols, right? Basically, we see the reduction of our carbonyls into into alcohols, right? Whether we're using carboxylic acids here, or even we saw way back in the chapter on ketones and aldehydes. That being said, there are reactions where you don't reduce that carbonyl. That carbon's oxidation number does not change. Okay, so you're essentially swapping out that OH part of your carboxylic acid for something else. But now think about what must be the properties of that something else in order to keep the oxidation state of that carbon the same, and in order to not have this be a redox reaction. Okay, well, think about oxygen, right? Oxygen's pretty electronegative, so you want the the atom here to be more electronegative than carbon. Okay, so that way it's still, if you were to cleave this bond heterolytically, this atom would get those electrons and therefore keep carbon at that same oxidation state. Okay, so that's something to keep in mind for these acid derivatives. All of them involve swapping out that OH group for something else, but that something else is also an electronegative atom or an electronegative group that's attached by an electronegative atom. Okay, so here are the different derivatives that we're going to look at. We've got acid halides. I think I may have referred to them specifically as acid chlorides, and you'll see that chlorine is probably the most common example you'll come across for acid halides. But that being said, you could have other halogens. We have acid anhydrides, esters, and amides. Okay, so that's actually listing them all out in order of reactivity. Actually, we'll talk about that in a second. But these are the main ones we'll come across. By the way, a nitrile group is also considered an acid derivative. Now, you're probably saying to yourself, wait a minute, there's no carbonyl there. Since the carbon has the same oxidation state, we do lump it in with this group. Okay, so even though it doesn't look like it would be an acid derivative, it will undergo a lot of the similar chemistry we're going to look at now. So I kind of mentioned in passing reactivity, and I mentioned that the acid halides and anhydrides are towards the left there, they were more reactive compared to the esters and amides, and because of that reactivity, you're probably not going to see them in nature. That being said, some of the other derivatives like esters and amides are more common in nature. You guys have actually seen esters before. We've made esters on multiple occasions. In one lab last semester, actually, I think if I recall correctly, I think we made isopentyl acetate. And this semester we've done a Fischer esterification of benzoic acid, right, to turn it into methyl benzoate, if I recall correctly. Okay, so again, esters are common functional groups that you might find naturally. They have a pleasant fruity smell. So a lot of fruits have esters present in them, and that's what accounts for their odor, for their smell. I guess aroma would be the right word there. Amides, like I said, are also very common. You can see that basically an amide bond is what connects amino acids together to form proteins. So that a peptide bond, so to speak, is the same thing as an amide bond. All right, the carboxylic acid in one amino acid does a condensation reaction with the amine group of another amino acid, and it makes this amide. All right, so that's what links together these proteins. All right, so let's talk a little bit, about nomenclature here. So for acid halides, you basically take the acid name and you replace the ic acid part with il halide. Okay, so acetic acid becomes acetyl bromide if you just swap out that OH group for a bromine. All right. Likewise, here we have benzoic acid. If we swap that out, it becomes benzoyl chloride. Okay. Now, if you recall, we had cyclohexane carboxylic acid, where that carboxylic acid group is not part of the ring, and therefore can't be called cyclohexanoic acid, right? We had to call it cyclohexane carboxylic acid, right? We had to give it a special name. In this case, we wouldn't just swap out the ic acid part. We actually change that whole carboxylic acid part into carbonyl halide. So here, if we swap out that OH for Cl, this becomes cyclohexane carbonyl chloride. Okay, so please note it's not just the ic acid part, but the ixyl acid part that gets changed. All right. In the case of acid anhydrides, if you're wondering where that name comes from, you could think of it as sort of the combination of two acids undergoing a dehydration reaction. So to make this a little bit easier to follow, I'm just going to use generic R's here. But let's say you had, some carboxylic acid here, and then another carboxylic acid. I'll call that an R prime group, just to show you it could be different. It need not be different. It could be the same, but if it is different, and essentially, if we remove H2O, right, we do a condensation reaction where we remove, water between these. So now this oxygen's connected to this carbonyl. This is what that resulting, acid anhydride looks like. Okay. Now, by the way, this reaction is actually kind of hard to do. We'll talk more about this later, but there you don't actually use a straightforward condensation reaction to make acid anhydrides. But that being said, that's kind of where the name comes from. It's two carboxylic acids missing a water molecule, hence the anhydride part of the name. Okay. So how do we name acid anhydrides? You put the prefixes of both acids in alphabetical order, and you just write anhydride in the name. Okay. If it's a symmetrical one, then you don't need to list both. You don't need to say it twice or put the prefix di or anything like that. You could, for example, if these were both acetate groups, if these were both acetic acids, you would just call this acetic anhydride, right? You don't have to say diacetic or acetic or anything like that. But if you do have different groups, like here we have, the combination of acetic acid and benzoic acid, this is called acetic benzoic anhydride. In the case of esters, esters are kind of the combination of an alcohol and a carboxylic acid. Again, you could kind of think of it as being like, to use the earlier example with a condensation reaction, you could think of your alcohol, combining with your carboxylic acid, and you subtract water, and that's where you get your ester from. So basically, what you've got is an alkoxy group attached to that carbonyl. The alkyl part of that alkoxy group comes from your alcohol. So we use the alkyl prefix to that as a prefix, and the suffix of the name takes the carboxylate name. Okay, so if this is an ethyl group and this is the carboxylate of acetic acid, so it's acetate, we would just call this ethyl acetate. Okay. So essentially, you're just taking the carboxylate name, the 8 form of the carboxylic acid, and we're just adding the alkyl group as a prefix here. All right. So it might help to identify your carboxylate group and identify which group comes from your alcohol. So it's always attached to the sp3 oxygen of your carboxylate group. Okay, so in this case, here's that oxygen, here's this ethyl group. Over here, you can see here it's a methyl group. Okay, and then you're going to name this part as if it were, the anion form of the previous acid. So here we have what would have been cyclohexane carboxylic acid. Instead, it becomes cyclohexane carboxylate, and we put methyl as a prefix because of that methyl group. Okay. Now here we have a dioic acid, malonic acid, and so we have two sites for forming an ester, right? In this case, they both are ethyl groups, so this becomes diethyl malonate. So again, we're using the anion form of our carboxylic acid, but because there are two sites for these esters forming, we have to use di for the for our alkyl group prefix. All right. Amides basically take your ic acid ending and replace it with amide. Okay, so acetic acid becomes acetamide. Okay, and so basically, to make an amide, you're just taking a nitrogen-containing group, essentially an amine, and tacking it onto a carbonyl. That's really all that's different. You're replacing that OH group with an amine of some sort. Okay, so benzoic acid becomes benzamide. Cyclohexane carboxamide is the equivalent of cyclohexane carboxylic acid, right? Again, you're replacing the here you're replacing the YL in carboxylic YLIC, the ilic part of carboxylic acid is completely replaced with amide. Okay, so that's a little bit unusual. I guess you're not ending just with the ic acid part, but you're going back to an extra vowel. All right. In regarding the pronunciation of amide, this is kind of probably confusing to a lot of chemistry students because I feel like I change my pronunciation of that word amide depending on the context. Because sometimes you'll probably have noticed that I refer to it as either an amide or amide or amide, and depending on who you talk to, that might be a little bit different. If it helps, in terms of my own consistency guide, in the case of the anion, so if you have sodium amide, I pronounce it amide, right? So you pronounce it with that inflection to designate the anion form. Okay. When I'm referring to the functional group, I refer to it as an amide functional group. But when I'm saying it in a name, I think just the pronunciation, just the cadence of the word, it sounds easier to pronounce it as amide. Okay. So yeah, it's basically, so amide for the anion form, amide for the amide form. So I apologize. I know that's probably a little confusing. And that being said, I'm sure, if you pronounce it weird, people will forgive you because there's 3 different ways to pronounce this one word. You'd hope that organic chemists could have been a little bit more creative with the usage of that word. But anywho. Okay, now I mentioned that for amides, you basically have an amine attached to your carbonyl, right? Well, in the examples we saw there was just a regular amide, right? We just end with that amide ending. Those were primary amines, right? What if you have a secondary or tertiary amine? Okay, well, basically what you do then is you treat any extra alkyl groups that are not connected to that carbonyl. Okay, so those other 2 groups are carbon-containing groups. You treat them as substituents, but to show that they are attached to the nitrogen and not part of your your parent chain, you have to put an N before them. Okay, so in this case, we have N-methyl acetamide to show that we've got a methyl group attached to the nitrogen and not somewhere on this carbon chain. Likewise, here we have two methyl groups attached to our nitrogen, and just like you would with any substituents you have attached to the same carbon, where you've got to use the locant twice, here you would say NN dimethyl acetamide. All right. Finally, we've got nitrile groups, and basically you just take the ic acid or oic acid ending and replace it with O-nitrile. All right, so acetic acid becomes acetonitrile, benzoic acid becomes benzonitrile, and so on. Okay, so I mentioned earlier that the different carboxylic acid derivatives vary in their reactivity, and I think I pointed out that they pretty much go in this order of acid chloride or acid halides, then followed by acid anhydrides, esters, and finally amides. Okay, now to understand this, let's look at those carbonyls. Let's look at their electrophilic sites, right? So remember, your carbonyl carbon is prone for a nucleophile to attack. We've seen that in the last couple of chapters, right? It's a pretty common place for our nucleophile to come in. And we'll see, like, again, a lot of repeating patterns here in the types of reactions that we look at. So what differentiates these in terms of reactivity, right? What causes these differences in reactivity? Well, in terms of what's different between them, of course, is just these groups attached to that carbonyl, right? So what's different about them? All right, so in order to understand this, let's break this down in terms of how these groups attached to our carbonyls are different in terms of inductive effects, in terms of resonance, steric effects, and of course how these groups behave as leaving groups. So let's start off looking at an acid chloride as an example, right? As something that's very reactive, an acid derivative that's very reactive. When we look at chlorine, keep in mind that chlorine is very electronegative. It's a period below oxygen and nitrogen, and so it's a lot squishier than your typical period 2 elements, right? And you've got to keep in mind that the lone pairs on that chlorine can be used in resonance. All right, so we can have those electrons from that chlorine swing over and give us another resonance structure here. Okay, so that being said, of course, this is not a very significant contributor. We don't have a like that chlorine doesn't like having a positive charge on it. But again, we've got another resonance contributor here. Okay, another thing to keep in mind, of course, is that that chlorine is a great leaving group. All right, so that chlorine being very large and squishy and capable of stabilizing the negative charge on it relatively easily when it leaves as a chloride ion is something that helps enhance that reactivity. Okay, now for the let's look at amides, right? In the case of an amide, when we look at the lone pair and the nitrogen, notice that lone pair is also involved in the in terms of the resonance here, right? But now the difference between the nitrogen and the chlorine is twofold. One, that nitrogen's much better at stabilizing a positive charge than the chlorine is, because it's it's not as large and squishy. And also notice that we have a pi bond here. Keep in mind that nitrogen and carbon are in the same period, so the p orbitals that they overlap to form that pi bond are the same sized p orbitals, whereas for chlorine it's using a 3p instead of a 2p orbital, so you don't have very good overlap there, right? So this this resonance contributor here is much more significant compared to that of having our chlorine. Also, NH2 is not a good leaving group. We've seen that amide ion is very reactive. We've seen it's a great base, because it's so reactive. It really wants a proton. So you can imagine that this is not very stable as a leaving group. Okay, so basically you could kind of think this is kind of like how aldehydes and ketones work. The only difference is that normally on an aldehyde or a ketone, you have a hydrogen or an alkyl group here in this sort of Z position. That's not a good leaving group, right? You're not going to undergo substitution there, right? Because those aren't good leaving groups. So that being said, in the case of a lot of these acid, these acid derivatives, though, because these groups are capable of becoming leaving groups, we do see a substitution here. Okay, so let's have a look at this substitution process in general. And again, you'll notice a lot of similarities between all these acid derivatives. They all kind of rely on a very similar mechanism, namely that the nucleophile comes in and attacks that carbonyl, which in turn swings those electrons up to the oxygen, right? Because that carbon can't have 5 bonds to it. When these electrons swing back down to reform the carbonyl, you could kick off the nucleophile and do the reverse of this reaction, or you could kick off that group, that Z group here, and that is what gives you the substitution that we observe. Notice that this is not a direct SN1 or SN2 substitution. We don't go through a carbocation intermediate like we do with an SN1 mechanism, and we do not have a nucleophile have our leaving group leaving at the same time as our nucleophile attacking, so it's not SN2. Okay, this is a basically a nucleophilic acyl substitution is the term we use here. And that's how we can swap out the group attached to our carbonyl. Okay, it has to go through this intermediate where the oxygen has a negative charge. Okay, so let's see an example. So here we have an acid chloride. Here we have an alkoxide group, a methoxide specifically. Okay, so that's our nucleophile that's going to attack that carbonyl. We have those electrons swing up to the oxygen, and here's the intermediate we form. Okay, now, out of these, which of these is the best leaving group? Well, this benzene is not going to be a good leaving group, right? You'd have this leave as a carb anion, and that's really reactive. You'd be taking out of aromaticity. Alkyl groups, R groups in general, are not good leaving groups, and in the case of a phenyl group, that's an aromatic group, it's going to be an even worse leaving group, right? So that gives us our chlorine leaving as a chloride, or our methoxy group leaving as a methoxide. It's kind of how it came in. Okay, out of those two, well, remember the chlorine is large and squishy. It's relatively electronegative. It's good at stabilizing that negative charge. So this is a great leaving group compared to the methoxide. Compared to the oxygen. So, and again, you can kind of think of this in terms of ARIO. Like we've seen this with carboxylic acids, or with organic acids in general. And you could kind of think of that oxygen stabilizing that negative charge compared to that chlorine stabilizing that negative charge. It's the A in ARIO, right? It's kind of the same logic you'd use to justify which acid is better based on the stability of its conjugate base, right? So hydrochloric acid is a much better acid than methanol for the same reason, okay, right? Hydrochloric acid has a pKa of -7. Methanol has a pKa of somewhere around like 15 or 16, right? So again, out of the two options here, the chlorine makes more sense to leave as a chloride. And that is why you wind up with the corresponding ester. Okay, and this, by the way, is also why acid halides are much more reactive than ester on that reactivity hierarchy we've seen for acid derivatives. Okay, I pointed out again earlier, this is not an SN2 mechanism, it's not an SN1 mechanism, so this slide just kind of, reiterates that. All right. Something to keep in mind for the mechanisms involved here. sometimes we have proton transfers involved. Again, keep in mind when you're looking at those mechanisms, be cognizant of your charges, right? Be wary of negatively charged, species in acidic conditions. Because remember, if you have protons floating around, they're probably going to protonate those negative charges, right? They're going to those negatively charged atoms are probably kind of basic. And vice versa with under basic conditions, right? If you have, watch out for any positive charges that might form, okay? Because you might have an extra proton, bases can pluck off extra protons. Okay, so let's look at some examples of proton transfers here. We have an ester being converted into a carboxylic acid here with water. Now, water, remember, is a pretty weak nucleophile, right? And so, here we have our two neutral species. They're pretty stable. They're pretty low in potential energy. And notice that our intermediate here, when we do a nucleophilic attack, is a zwitterion. We have a negative charge on this oxygen and a positive charge on this oxygen. This yields a very high activation energy, right? Going from this really stable, low energy reactant or reactants to this very high energy transition state, or intermediate over here, but you have a pretty high transition state as well. You've got a very, very large activation energy to overcome. Okay, so a nucleophilic attack in this situation is probably not the best way to go. So instead, what we're going to do is we're first going to protonate our ester to begin. Okay, and of course, this is when this occurs in an acidic solution. We'll talk about what happens in a basic solution in a little bit. But once you've protonated your species, notice that our charged reactant now is higher in potential energy, and this, of course, shrinks our activation energy. All right. It also makes our intermediate a little bit more stable. All right. Notice that we no longer have our zwitterion. We have only a positive charge in this oxygen. Again, probably you don't want to have a positive charge in an oxygen, but it's better than having that zwitterion in an acidic solution. Okay. So if this were done in a basic solution, on the other hand, now we have a base, or hydroxide ions floating around. If we used a metal hydroxide here, that's a much better nucleophile than water, right? So we can go ahead and have that act as our nucleophile. Okay, since hydroxide is less stable than water, that raises the energy profile of our reactants, and again, that lowers our activation energy. Okay, once again, also notice that our intermediate is not a zwitterion. We have only a negative charge in this oxygen. Okay, which again is okay because we're doing this in a basic solution. Okay, so that being said, it is possible to have neutral nucleophiles as as our nucleophiles. Even though we've seen that sometimes it's better to have charged species, charged solutions. But keep in mind, of course, that this will probably lower our reaction rate, since we're dealing with things that are less reactive and that will have higher activation energies you've got to overcome. All right. Plus, keep in mind that transition, or the intermediate rather, is going to be a zwitterion. Okay, so with that in mind, the fact that proton transfers aren't just nice, but they're sometimes necessary to get a reaction to occur, keep in mind that you may have up to 3 proton transfers to include when drawing out your full mechanism. Okay, so let's try an example here. So here we have an acid chloride reacting with water to make the corresponding carboxylic acid. Okay, so see if you can, pause this video, see if you can draw out the mechanism for it before we go over it in the next slide. Okay, so if you're back, let's have a look. You can see here we have our pretty reactive acid chloride, so we have water coming in as our nucleophile. Even though it's a weak nucleophile, this is still capable of reacting. Again, you're going through a zwitterion intermediate, but I think this is one of those examples where, like I said, given the reactivity of our reactant, even though we have a neutral nucleophile, that helps speed up the reaction a little bit. Again, makes it a little bit more feasible, right? You probably wouldn't want to do this with anything less reactive than an acid chloride. But anyway, so when these, our nucleophile attacks that carbonyl carbon, these electrons have to swing up to the oxygen. When they swing back down, it kicks off the more stable leaving group. So our chloride here leaves. Chloride, of course, slightly basic. It can pluck off a proton and, basically turn this positively charged intermediate into the neutral product. Okay, and of course we have hydrochloric acid as our byproduct. Okay, so yeah, and of course you have to keep in mind that these steps are all reversible. Again, we've seen that chloride's a great leaving group. Water is a good leaving group too, so it is possible to also kick off water and just do the reverse of this reaction. This reaction here is definitely very reversible, and so basically each of these steps are, chloride could act as a nucleophile here as well. Yeah, and one thing to consider from a synthetic standpoint that might push your equilibrium to the right, if these are all reversible reactions, is to basically try and drive this reaction forward by taking away a product, right? And so it'll drive to the Le Chatelet's principle will have the equilibrium shift to the right to make more hydrochloric acid if you absorb that hydrochloric acid. So having a base present, let's say a weak base like pyridine, for example, would be great for shifting this equilibrium to the right. A pyridine would soak up your HCl and probably get it to precipitate out as pyridinium chloride. All right, let's try another example here. So go ahead and pause this video and see if you can draw out the mechanism for this. Here we have an acid anhydride. It reacts with an alcohol, so we have an alcohol here as our nucleophile, and that's what splits this up into the two corresponding esters. Okay, so if you're coming back from pausing this video, let's see our full reaction here. So our alcohol nucleophile, of course, attacks one of our carbonyls. Now, if you're trying to figure out which of these two carbonyls is more reactive, from a steric standpoint, this one on the right is more likely to react, right? You don't have that bulky tertbutyl group in the way. If you have, if you look at this one over here, you only have a methyl group. So you're probably going to attack that carbonyl first. And again, you should see that pattern where these electrons get kicked up to that oxygen. When they swing back down, they get the other leaving group to leave. Now, the good leaving group that we have here is going to be this this anion that's going to leave this carboxylate anion. So when you break this bond here, you get an anion that's resonance stabilized, right? That negative charge is actually spread out between both oxygens here through resonance. Okay. Of course, this is a decent base. It plucks off the proton from this intermediate here to give us the neutral product. Okay. And then, of course, you can do a second round of this reaction. You can have our alcohol attack this carbonyl, and again, send those electrons up. They'll come back down and kick off, your OH group. Now, what would make this more feasible, if this is done in acidic conditions, of course, would be to have a protonate that OH group first. That'll make this a better leaving group for that second step. Okay, so let's talk about acid chlorides. We've seen that out of all of these acid derivatives, the acid chlorides are probably the most readily reactive, and therefore they're going to be very, very useful for making products. They're a really good starting point for making other products. So we make acid chlorides through reacting a carboxylic acid with thionyl chloride. So thionyl chloride is SOCl2, right? So basically your pi electrons in your carbonyl act as a nucleophile here and actually do a nucleophilic attack on the sulfur of your thionyl chloride. So it's kind of almost a little bit backwards, right? You're kind of treating the sulfur like our carbonyl here, and that's where the nucleophilic attack's occurring. These electrons swing up to this oxygen, and when they swing back down, they actually boot off a chloride, okay, from your thionyl chloride, and they make this intermediate. Okay. Now, for this intermediate, when you can deprotonate that oxygen that's charged and make this neutral intermediate, you've got a very stable leaving group here. Okay, basically, if you pluck off a so if you have another nucleophile come in and do a nucleophilic attack on this carbonyl over here, when those electrons swing back down, this is a great leaving group. You break that bond pretty easily. And what drives this forward really, really well is that basically when this kicks off a chloride, you get sulfur dioxide gas, right? And so that can bubble away. This is a nice neutral molecule, and and there you go. All right. Again, as we've seen before, having a weak non-nucleophilic base like pyridine is also very helpful in driving this reaction forward. Okay, so let's have a look at some reactions of acid chlorides. One reaction that we've already looked at is hydrolysis. We've seen that your acid chloride will react with water to form the corresponding carboxylic acid. Okay, so again, you have water here as your nucleophile, which we've seen that, neutral nucleophiles aren't the best. Water is not a great nucleophile, but given the reactivity of our acid chloride, this reaction is possible. Okay, so when these electrons swing back down, they kick off the chloride, and of course we can deprotonate the resulting, intermediate to give our neutral product. Okay, so again, because your acid chlorides are so reactive, we can use it to make other acid derivatives, not just carboxylic acid. So if we use an alcohol instead of water, we can basically turn this into an ester. We swap out that chlorine for an alkoxy group, okay, and we've made our ester. So this is called alcoholysis. So it's like hydrolysis, but we're using an alcohol instead of water. Okay, so here's the full mechanism again. Again, you'll notice a lot of similarities to what we just saw with water. The only difference is instead of water, you've got an alkyl group on that oxygen. Okay, but otherwise the mechanism's pretty much the same. Okay, so instead of an alcohol, if we use an amine or ammonia, we have what's called aminolysis, or aminolysis, I guess is probably the better way to pronounce that. You make an amide, right? So if you use ammonia, you make the primary amide. If you use a primary amine, you make the secondary amide. If you use a secondary amine, you make the tertiary amide. All right, so yeah, basically it's you're essentially swapping out the chlorine for, you're getting that nitrogen to bond to your carbonyl carbon, and you lose HCl in the process. Okay, so again, this can be driven forward. Having pyridine present, it'll probably help drive this forward. Okay, that being said, you also have lots of amine present that's also a base in its own right, so you probably don't need something separate. All right, so here we go. Here's our full mechanism. Our amine is our nucleophile. Again, attacks our carbonyl, swings those electrons up. Those come back down, kick off the chloride. And again, like I said, you don't actually need pyridine. You could use you have plenty of this amine reagent floating around that can deprotonate your intermediate to give the neutral amide product. All right. So we've seen lithium aluminum hydride as a reducing agent. Again, we can keep in mind that the hydride there is a nucleophile. When you use that as your nucleophile, you basically convert your acid chloride. You're swapping out that chlorine for a hydrogen, so you're making an aldehyde. Now, that being said, remember, lithium aluminum hydride is a strong reducing agent, right? So this aldehyde doesn't stay an aldehyde. You have another equivalent of hydride come in and reduce that aldehyde further to the corresponding alcohol. Okay, so you get a primary alcohol. You can reduce your acid chloride completely to a primary alcohol the same way you can reduce a carboxylic acid to a primary alcohol using lithium aluminum hydride. Okay, now that being said, what if we want to stop at the alcohol, right? Or sorry, stop at the aldehyde instead of proceeding all the way down to the primary alcohol? To do that, we need the reducing agent version of PCC. So if you remember, chromic acid is a strong oxidizing agent. It would oxidize a primary alcohol all the way to a carboxylic acid. If we used pyridinium chlorochromate, which is kind of a modified version of chromic acid, we could stop at that aldehyde, right? So in a similar way, instead of using lithium aluminum hydride, which is a really strong reducing agent, would take us straight to the primary alcohol, we use a modified version where instead of lithium aluminum hydride, where there are 4 hydrogens on our aluminium, we have 3 bulky alkoxy groups on our aluminium. All right. Now, so an example of a bulky alkoxy group here would be tert-butoxy groups. Okay, so you've got these bulky tert-butoxy groups on our aluminium, and that kind of limits access to that aluminium, and kind of limits, how much hydride it can sort of give to your product, to your intermediate. Similarly, we can have a carbanion nucleophile. So if we use a Grignard reagent, instead of a hydride attacking our carbonyl, we have a carbanion, so we have a carbon-based nucleophile. Again, just like with hydride, your carbon, your alkyl group is going to be a lousy leaving group. So you kick off the chloride and you wind up with the resulting ketone instead of an aldehyde. Now, just as your lithium aluminum hydride doesn't stop at the aldehyde, it goes on to the primary alcohol, your Grignard reagent will not stop at the ketone. If you have excess Grignard, a second equivalent will attack the carbonyl of your ketone and convert it into the resulting tertiary alcohol. Now, just as we use a bulky version, or like a version of the lithium aluminum hydride with a bulky substituent on it to limit your reaction, to stop it at the aldehyde, we can kind of do the same with our Grignard. Instead of using a Grignard, which is very reactive, which will drive the product towards the alcohol, we can instead use a Gilman reagent. Okay, so a Gilman reagent is like a Grignard reagent, except instead of magnesium, our metal center here is a copper. Okay, so that copper carbon bond that we form is going to be less ionic than the carbon-magnesium bond you would see in a Grignard reagent. Okay, so copper is less electropositive, I guess, than I guess is probably the best way to explain it. Kind of the opposite trend of electronegativity, but that results in that bond being less ionic. There's less of a difference in electronegativity between carbon and copper than compared to carbon and magnesium. Okay, so as a result, if you have less ionic character to that bond, then your carb anions like less nucleophilic. All right, so here's a summary of all of the reactions we've seen. Again, this might be a good picture to have on a flashcard while you're studying or while you're doing practice problems, just to kind of internalize these. But yeah, notice again that starting from our acid chloride, we have a lot of synthetic utility here. There are a lot of options for things that we can turn our acid chloride into. All right, so let's practice that. Go ahead and pause this video and see if you can fill in the reagents for each of the steps involved here. Okay, and so if you're back now after having paused the video, let's fill in the answers. Okay, so here you can see we start off with a carboxylic acid group and we convert it to an acid chloride. Okay, so we're swapping out the OH in that carboxylic acid group with Cl. So we know that we need thionyl chloride for that. Next, we are going to convert that, we take that carbonyl, instead of a chlorine coming off of it, we have this cyclopentyl group. Okay, so we're essentially adding on a carbon-containing group. So immediately the thing that should come to mind here is using a Grignard reagent, right? So using a Grignard reagent, we'll tack on that alkyl group. Now, we've seen that Grignard reagents can go on to the resulting alcohol, right? If we get a second equivalent here, we would get two cyclopentyl groups, and this would be an OH group. So you might want to use a Gilman reagent instead of a Grignard reagent. That being said, I think they were comfortable here with using a Grignard because these groups are so bulky that kind of limits the access of another nucleophile here. So you probably get a decent yield of just this ketone product. Okay, but that being said, if you had smaller alkyl groups involved here, you might want to reconsider your choice of a Grignard reagent here and instead, pick a Gilman reagent so that you stop at, the carbonyl and then go on to the alcohol. Okay, over here we can see that we've made an amide, right? So that's with a nitrogen nucleophile, so we need the corresponding amine that tacks on this piece here. So there's that amine. Okay, so just add a hydrogen there. We've got two carbons coming off of this, that are not the ones attaching it to the carbonyl. So that means you had to use that secondary amine to carry out this reaction. All right, so on to the next acid derivative, and that's anhydrides. Now, I mentioned one way to sort of conceptually think of anhydrides is of two carboxylic acids that undergo a condensation reaction with each other. Okay, so you can see here, for example, we have two molecules of acetic acid. Well, there's only one drawn here, but imagine that we have another one reacting with it, and we remove H2O between it. Here's the water we lose, and there's the resulting anhydride that's formed. Okay, now notice that in order for this reaction to work, we've got to heat this up to 800 degrees, which is kind of like a textbook definition of harsh conditions, right? This is a pretty tough reaction to do, and that can be, just very detrimental to any product you want to make, right? At that temperature, you might cause, whatever product you're trying to make to decompose into something that's not the product you want. So clearly this is not the optimal way to do this. Okay, so instead, we have a reaction that we saw earlier. We can look at our acid chloride, which we've seen as a very reactive starting point. It's great for making all these other acid derivatives. And we're just swapping out the chlorine for this, this acetate group. Well, I guess really just any carboxylate group here. We've got a generic R here. But in the previous example, we would have had a methyl group here to make acetate. Okay, so again, this is nucleophilic. It'll attack that carbonyl carbon, and of course, do the reaction we've all seen where when these electrons swing back down, kick off the chlorine as a chloride ion, and produce our acid anhydride. Okay. Oh, quick note here. With acetic anhydride, we've seen that, both R groups are the same, but remember that need not be the case. We can have an asymmetric anhydride. Okay, so we can have different R groups depending on what acid chloride you use and what carboxylate anion you use. Okay. So yeah, in terms of leaving groups, again, chloride and acetate are both great leaving groups. Or say any carboxylate is a good leaving group for different reasons. Chloride, as we've seen, is a large squishy atom, pretty electronegative, great at housing that negative charge. In the case of your carboxylate, that negative charge is spread through resonance between both oxygens. All right, so think back to Ario, right? And think back to are acids and bases, right? An acid is a better acid, based on how stable its conjugate base is. How good is it at housing that negative charge? And ARIO is that acronym that helps you remember the sort of hierarchy behind that. So the A in ARIO is atom. Okay, an electronegative atom, a large squishy atom like chloride, would be great at holding that negative charge. But next on the list is R for resonance, and again, your carboxylate ion is really good at holding that negative charge due to resonance. Okay, not as good. Hydrochloric acid would have a pK around -7, whereas we've already seen that carboxylic acids have pKs around 4 to 5. So, obviously there's a significant difference there. But that alone will tell you then that, chloride's a better leaving group, and that's why acid chlorides are much more reactive. Okay, so in terms of the reactions we see, they're pretty similar, right? And they work on the same principle as we've already seen. You have your nucleophile coming in, attacking a carbonyl, and kicking off that leaving group. So here's a summary of all the reactions that you can do. Again, very similar to what we've seen with acid chlorides. Okay, so one major difference to watch out for when you are designing syntheses involving acid anhydrides, and when you're trying to draw out mechanisms for these reactions, you do not need a weak base like pyridine to help deprotonate things. Okay, you have to remember that the leaving group you have here for your acid anhydride is a carboxylate ion, which remember is a conjugate base of a weak acid. So it's a decent weak base itself. So it kind of fills in the function of your pyridine. You don't actually have to add an extra base. So one common reaction we actually see with anhydrides is to use acetic anhydride to add an acetyl group to another molecule. So, for example, you could add it to react it with an alcohol to make the corresponding ester, or you can react it with an amine to make the corresponding amide. Okay, so again, very similar synthetic utility to what we saw with an acid chloride. Okay, so and that's often the case with a lot of pharmaceuticals. So, for example, to make aspirin, which is acetyl salicylic acid, we take salicylic acid and react it with acetic anhydride, and that gives us aspirin. All right, so that's actually why over time, if you have an old bottle of aspirin, it smells a little bit like vinegar because the reverse reaction sometimes occurs, and you have aspirin degrade back to salicylic acid, and you get acetic acid, or the active ingredient in vinegar, as a byproduct. Okay, here you can see that if we take aminophenol, and we react with acetic anhydride, we can make the corresponding amide here. Okay, and so and that's basically Tylenol. Okay, on to esters. So Fischer esterification is actually a reaction you've seen in the lab, and it's a common way to combine a carboxylic acid with an alcohol to convert them into the corresponding ester. So for this to work, you have to use an acid. You need protons to catalyze the reaction. So you actually start off with a proton transfer. Remember, carboxylic acids aren't as reactive as acid chlorides or acetic acid anhydrides. So it helps to protonate your carbonyl oxygen to raise its potential energy and make it more reactive. Okay, so your alcohol comes in as your nucleophile, the oxygen on that alcohol, I should say, that kicks these electrons up here, converts this into a neutral alcohol group, and of course this species is it has a positive charge on that oxygen because of that hydrogen, so you can just deprotonate that. And there's the corresponding intermediate that we make. So if we've got two alcohol groups and an alkoxy group on there. Okay, so then you can protonate one of those alcohol groups and turn them into a better leaving group, right? That can leave as a water molecule when these electrons swing down and reform that carbonyl, which you can then deprotonate to give you the your ester product. Please note that all of these reactions are reversible. Okay, so that affects things like the the yield of your product as well as the rate of the reaction. Okay, so since this is an equilibrium process, you might want to think about how do we drive this reaction forward? How do we get more product out of this equilibrium? Okay, so if you think about the concentration of your reactants, that might be one thing that can help drive this forward. Also think about things that might remove your products. So notice that you're making water as a byproduct, right? This is kind of a condensation reaction, right? You're moving, the OH from your carboxylic acid and a proton from your alcohol to make the corresponding water here. So if you have something that soaks up water or kind of dehydrates this, that would also drive this equilibrium forward. Okay, so another way to make esters, as we've already seen, acid chlorides are a really good starting point. So if you react them with an alcohol, they'll make the corresponding ester. Of course, we can also do this with an acid anhydride. Okay. Now, what about reactions of esters themselves? Well, you could take an ester and in the presence of a strong base, right? So if you have a metal hydroxide, that hydroxide ion works as a nucleophile, right? It can do a nucleophilic attack there and essentially drive off that alkoxy group and form the a carboxylic acid, right? So kind of you go back to a carboxylic acid this way. This is kind of the reverse of Fischer esterification. Okay, please note that we use a base here instead of an acid to carry this out. Okay, now this is called saponification because this is actually the process through which we make soap. When you think about fats, right, animal fats, triglycerides, that's essentially an ester, right? So a triglyceride is made of glycerol, which is a triol, right? It's an alcohol that has 3 alcohol groups in it. And it's got fatty acids, which are long-chain carboxylic acids, and those are held together by ester bonds. So what you do is you react that with sodium hydroxide, with lye, which is just a concentrated solution of sodium hydroxide, lye spelled Lye. And that will carry out saponification and convert your carboxylic. It'll take the glycerol and separate it out, and you, instead of getting the carboxylic acids in their protonated form, you actually wind up getting the sodium salt of those fatty acids, and that's basically what soap is. Okay, so that's essentially what's going on. Again, you can kind of use Le Chatelet's principle here to help kind of push this forward as well. Okay. Now, saponification occurs under basic conditions, right? Remember, the goal is you're trying to make that salt of those fatty acids. That's what soap is. That being said, you could also catalyze the reaction under acidic conditions. Okay, so you can do an acid hydrolysis. The difference here is that instead of getting the carboxylate of those fatty acids, instead of getting them in their salt form, you wind up getting them in their protonated acid form. All right, so here's an example of the acidic hydrolysis of an ester. Okay, so here's our ester that we're starting off with. Again, we're doing this under acidic conditions, so it might help to protonate that oxygen, and you can because you're doing this in acidic conditions. You got plenty of protons around, so you protonate that oxygen to make that more reactive. So now water, which isn't a great nucleophile, is your nucleophile. It attacks that carbonyl, kicks those electrons up to that oxygen, when they you know, you can actually deprotonate that water to make a neutral intermediate, right? So that's a little bit more stable, but eventually you want to have a good leaving group here to continue on with the mechanism. So it helps to protonate the alkoxy group you're going to get rid of. And so when these electrons from that oxygen swing back down to reform that carbonyl, that alkoxy group leaves as an alcohol. Okay, so you lose an alcohol group, and you can deprotonate this intermediate to give you the neutral carboxylic acid product. Again, please note that this is the protonated version of the carboxylic acid. Okay. Just in the same way, instead of, if we use an amine instead of a water to carry out our, we use water for hydrolysis. If we use an amine, we can make an amide through aminolysis, right? So we're kind of cleaving that alkoxy group off. It takes one of the hydrogens from your amine, or ammonia as this case might be, to make the corresponding alcohol, and you've now tacked on that amine or ammonia as part of that amide functional group. Okay. A quick note here about this kind of aminolysis. Again, please note that we've gotten to esters. We've gone through acid chlorides, acid halides, and acid anhydrides, which are much more reactive. Now we're getting to esters and amides, which are less reactive. So from a synthetic standpoint, this might not be as useful. Okay, if you were starting from scratch, it would be better to start off with an acid chloride, right? It'd be much more reactive. You're probably going to get your product in a larger yield and quicker. Okay, but that being said, if you are dealing with an ester from previous reaction, this is a way to convert it into an amide. Okay. Regarding other reactions of esters, we can reduce them using a strong reducing agent like lithium aluminium hydride. In this case, it reduces it all the way down to the primary alcohol. Okay, so I think we may have talked about that earlier. I think in the last chapter when we first talked about lithium aluminium hydride, I think we may have had an example there. With an ester. But anyway, even if not, the key thing here is that esters, like carboxylic acids, will get reduced all the way down to a primary alcohol. Okay. Now that being said, you need to have excess lithium aluminium hydride. Some of it provides a hydride nucleophile. Some of it actually acts as a base. All right, so that's something to keep in mind. Okay. So yeah, so you actually wind up getting two alcohols. Something to keep in mind there. The alkoxy group of your ester leaves as one alcohol. So here, notice we have a methoxy group, so you get methanol as a product. And the rest of the molecule, of course, becomes a primary alcohol. So you kind of cleave around this carbon-oxygen bond, and this part of the molecule becomes an alcohol. Okay. Now, we saw that it's possible to stop our reduction and not have it go all the way to a primary alcohol. We could stop at the resulting aldehyde, for example, when we did this with carboxylic acids. With a ester, we use what we call DIBA, right, which is diisobutyl aluminium hydride. So you have these bulky isobutyl groups on your aluminium, and just like with your tert-butoxy groups, which are very bulky, it kind of limits access to that aluminium, limits access, the ability of that aluminium to give away hydrides, and therefore you wind up stopping at the aldehyde product. It doesn't go all the way to a carboxylic, or it doesn't go all the way to a alcohol. Okay, so something to keep in mind if you are starting with an ester, but you want to stop at an aldehyde. Okay, so yeah, here's the mechanism of an ester with your lithium aluminium hydride. Just like that, we could also react with Grignard reagents. Just picture, instead of a lithium aluminum hydride, we're using a magnesium, carbanion species, and that carbanion is our nucleophile instead of a hydride. Okay, so we have an R group here instead of a hydrogen, and we would make the ketone instead of the aldehyde. Okay, so yeah, so basically we this slide actually is talking about Grignard reagents and talks about how you go on to make a tertiary alcohol, but it's showing you how it's showing you the mechanism for lithium aluminum hydride going to the eventual primary alcohol. The key thing is it's just showing how hydrides, you add multiple hydrides to that carbonyl carbon to give you the resulting primary alcohol. Okay, so with that in mind, here we have an ester starting off, two ester functional groups actually. So pause this video and see if you can list out the reagents you would use to convert this ester here in the middle into these alcohol products on either side. Okay, so if you're back, here are the answers. So notice that in order to do this, we open up the ring, obviously, when we do when we hydrolyze these bonds. But the other thing to realize is what are you cleaving off, and has the carbon skeleton changed? Okay, so notice that we have two methyl groups being added on here, right? So that tells you that we have some sort of methyl Grignard reagent attacking this carbon, which used to be a carbonyl. Okay, if you're having trouble seeing this, it might help to label your carbons on your ring and in your products to see, kind of map out which ones are which. Okay, over here we don't have as many carbons, but very similar reaction. The only difference is, instead of methyl groups here, we have hydrogens. So that should hopefully give away that this used lithium aluminum hydride as its reducing agent. Next up, we have amides. Again, this is very useful. We've seen that these amide bonds are very popular in nature, in proteins, but even in from a synthetic standpoint, we have a lot of materials that rely on this. For example, nylon. Nylon's a polyamide. We just take a diacid halide and a diamine, right? And we kind of use them to link together just multiple units, right? So these are kind of like AB polymers, right? So we just kind of link them together like that. All right. Incidentally, so this is a polyamide. Polyester is very similar. It's just that you have an ester bond instead of an amide bond. So you have an oxygen here instead of nitrogens. Okay, so basically we can take amides and hydrolyze them back into carboxylic acids. This can be done with dilute acid, but of course this is a very slow reaction. It requires a high temperature, so it's not very easy to do. It's definitely not feasible, but typical. This is a very similar mechanism to what we've seen already for the acid hydrolysis of an ester. Okay, the only difference, of course, is we have a nitrogen group breaking off, so this leaves as an amine, or rather an ammonium ion, as opposed to an alcohol. Okay, so here's the full mechanism. Again, you just protonate your carbonyl oxygen to make it more reactive. You have water coming in as a weak nucleophile. Kicks those electrons up to that oxygen, making that neutral. You can deprotonate that oxygen to make a more stable intermediate here. You can then protonate that nitrogen to make it a better leaving group. So when those electrons from that oxygen swing back down to reform that carbonyl, you kick off that amine as a leaving group. All right. Please note how many high-energy transition states we're dealing with here. We've got a lot of reversible reactions here. So as a result, that's a lot of steps to to kind of control and have be reversible. Okay, so yeah, basically you can also do base hydrolysis. Uh, again, this is also a slow process. But once again, I think we've kind of established that amides are towards the bottom of our acid derivatives in terms of reactivity. Okay. Um, Lithium aluminum hydride, of course, really strong reducing agent, can take your amides all the way down to an amine. So notice that we basically remove our carbonyl, we replace the oxygen with two hydrogens. Okay, so we get that corresponding amine. So basically your hydride comes in and attacks that carbonyl, kicks those electrons up. When your lone pair of nitrogen swings back down, and it kicks off the carbonyl oxygen, which is complex or attached itself to the aluminium. So this is a good leaving group. All right, so you kick off that leaving group and you form an imine intermediate. You add a second equivalent of hydride to that, and that, of course, makes this neutral and gives you the regular amine. All right, and then finally we have nitriles. So remember, nitriles, even though they don't have a carbonyl group, are the carbon in your nitrile is in the same oxidation state as your carbonyl carbon in all of these other acid derivatives. Okay, so to make a nitrile, we've seen that we can prepare them by just doing a substitution reaction, right? So if you take a primary or secondary alkyl halide, you can just do an SN2 substitution using a cyanide ion. Okay, so using sodium cyanide, that cyanide ion is a good nucleophile, and it'll kick off your leaving group in your alkyl halide and give you the resulting nitrile group. Okay. Another way to make a nitrile is to dehydrate an amide. So one way to do that is to use thionyl chloride again. Instead of making an acid chloride here, we are going to basically pluck off the oxygen and the hydrogens on our nitrogen. So we pluck off the oxygen on our carbonyl, the hydrogens on our amine of our amide, and basically form a triple bond between that carbon and that nitrogen. Okay. Other byproducts include sulfur dioxide and HCl, and again, those are very stable, easy to remove products. This just bubbles away, and so that's what drives this reaction forward. All right, so here's the full mechanism if you'd like to see it. Again, you should recognize a lot of things in common from the formation of an acid chloride, right? So again, your pi electrons on your carbonyl are the nucleophile here on that sulfur. We're going to have a really good leaving group here. And so when these electrons, you have a base come in and deprotonate that nitrogen, when those electrons, swing down here, they help form the starts of a triple bond. But basically we have our lone pair and our nitrogen, and so this whole thing is neutral. But basically, if we deprotonate this proton, now we form that triple bond, right? These electrons go towards forming the triple bond, and of course, then this carbon has too many bonds, so this bond has to break and kick off that chloride, which again gives us that very stable sulfur dioxide and drives this equilibrium forward. All right. So we can hydrolyze nitriles, and that's again a very useful reaction when you're starting off with a nitrile group. And so to do that, we can, using acid and heat, we can basically convert it to the corresponding amide, and then as we've seen, we can convert that further into the corresponding carboxylic acid. Okay, so here's the full mechanism, starting with our nitrile group, going all the way to our carboxylic acid. Okay, so I know this is a long mechanism, but basically we walk all the way sort of in a serpentine pattern here, towards that carboxylic acid product. So we start off with our nitrile here, and again we're dealing with a neutral species here and a weak nucleophile in water, so it helps to protonate our nitrogen, to protonate our nitrile. Again, we're doing this in acidic conditions here. It's an acid hydrolysis. So we protonate that, making it a little bit more susceptible to attack from that weak nucleophile. You can deprotonate the resulting intermediate to make this more stable. You then want to protonate your nitrogen. You're eventually going to have your nitrogen come off as an ammonia, so you're going to have a lot of steps where we're gradually going to keep on protonating that nitrogen. So we basically protonate that nitrogen, you deprotonate the oxygen, and you've essentially kind of reformed that carbonyl, or sorry, no, you formed the carbonyl. You've kind of taken away the multiple bonds to the nitrogen, and you have an amide effectively, right? So this is that amide intermediate that we've reduced our nitrile down to. Okay, or not really reduced, but kind of rearranged, I should say, because that carbon is still in the same oxidation state. So we have converted our nitrile into our corresponding amide, and then we can just hydrolyze that amide. So again, you protonate the carbonyl oxygen on your amide, making it more susceptible to a nucleophilic attack from your weak nucleophile water. That swings those electrons up here, making them more stable intermediate. It helps to deprotonate that oxygen, again, making this more stable. We're going to protonate that nitrogen. It's going to be a good leaving group now to leave as ammonia when these electrons swing back down. And there you can see we have the protonated version of the carboxylic acid, which you can then just deprotonate to make the neutral product. All right, so that was a long mechanism, but you can hopefully see some patterns there in how we eventually, get rid of that triple bond between the nitrogen and the carbon, and instead add hydrogens to that nitrogen to make it leave as our ammonia. Okay, now that was with acid catalyzed hydrolysis. We can also do that with a base. So if we use sodium hydroxide, remember here we have hydroxide as our base. That's also a nucleophile, right? So we can have our hydroxide attack that nitrile carbon and eventually wind up becoming the OH part of our carboxylic acid. Okay, so here's the mechanism for that. We have that nucleophile attacking the carbon. It kicks the electrons to the nitrogen. You're making this sort of imine, which you can then have a second equivalent of if your hydroxide attack that carbonyl. Sorry, not a carbonyl, but that sp2 carbon, and so you wind up with this intermediate here, which you can protonate to become more stable. And now notice that you have an NH2 group, right? So you can if you kick off a hydroxide leaving group, so hydroxide's almost kind of catalytic here, but you kick off your hydroxide leaving group and you reform this carbonyl, there's our amide intermediate. We can then take that amide and hydrolyze that further. As we've already seen, we can just take, you have hydroxide as a nucleophile again to that carbonyl, and you eventually, if you protonate that nitrogen to make it an ammonium or ammonia, you can have that leave as your leaving group, and you've replaced it with that OH from your hydroxide, giving you that carboxylic acid product. Okay. All right. So next, we've seen that we can get carbanion nucleophiles from Grignard reagents, so that can effectively attack our nitrile carbon, all right, and make this sort of imine product, imine intermediate. This can then be hydrolyzed into a corresponding ketone. So this charged nitrogen gets replaced with a neutral oxygen. We actually talk about this back in chapter 20. If you recall, we could cleave imines and enamines along that carbon-nitrogen bond to give us the corresponding ketone or aldehyde, as well as an amine. All right. So we can also reduce nitriles using excess lithium aluminum hydride. It'll just reduce it down to the corresponding amine, right? So we just basically add hydrogens to that nitrile carbon. We add hydrogens to the nitrogen of our nitrile. So essentially, we're adding hydrogen kind of across this triple bond, where across the two pi bonds of this triple bond, we're just adding two hydrogens to the nitrogen and two to the carbon of our what used to be our nitrile. Okay, so I've thrown a whole bunch of reactions at you in this chapter. Hopefully, again, you've started to notice some patterns, and that'll help memorizing them a little bit easier. That'll help make memorizing them and internalizing that a little bit easier. In terms of overall approaches, though, remember when we look at syntheses, the way you want to approach this is, how is my carbon skeleton changing? Am I adding carbons? Am I removing carbons? And then, are there any changes in functional groups? What functional groups am I going from? And what functional group do I have in my product? So what's changed? So to summarize all of the reactions, here we have kind of the general pathways of the different types of functional groups, right? So starting off with carboxylic acids, notice that we have acid chlorides, we have acid anhydrides, esters, amides, and nitriles, and there are the ways to get between all of them. Okay, notice that we have lots of arrows going down this way. Remember, your acid chloride is a really good starting point for a lot of these reactions. Though, keep in mind, on a quiz or exam, it might not be one of the options, right? You might have an acetic anhydride. So be ready to see that as well. But if you are designing your own synthesis from scratch and you have access to an acid halide, that's probably a good place to start your synthesis design. Okay, so let's pause and try that out. Okay, so here we have this reactant. We're trying to make this product. Identify the differences and see if you can figure out the reagents. So if you're back, you'll see that we've gone from a nitrile group here to the resulting aldehyde. Okay, now there isn't really a way to do this in just one step. So if we go back, you can see that we're starting off with a nitrile group here, and we're trying to wind up with an aldehyde over here. So there's no direct pathway between those two functional groups. So it actually helps to kind of hydrolyze that nitrile and convert into an acid chloride eventually, and then have that get converted into an aldehyde using your bulky lithium aluminum hydride. Okay, so that's kind of what happens, right? So we hydrolyze it with dilute acid, and then when we use thionyl chloride to convert that into our acid chloride, and then we can use our bulky tert-butoxy lithium aluminum hydride to convert that into the aldehyde and stop there. Okay. Remember, you can't use regular lithium aluminum hydride because that would go on to make the primary alcohol. Okay. So when it comes to changing the carbon skeleton, okay, how did we see carbon skeletons changing? Well, if you want to tack on carbons, one really easy way to do that is through a Grignard reagent, right? We've seen that all of these, all of the chemicals we've looked at here, all of our reagents, our starting materials, are carbonyl compounds. So it makes sense that we want to have some sort of nucleophile here with carbon in it, and that will extend the carbon skeleton from that carbonyl carbon onwards. So whether you're using a Grignard reagent or a Gilman reagent, you're adding on carbons, and that's more carbons than you started with, and so you've changed the carbon skeleton. Okay. Um, in the case of, in some cases, you can actually extend the carbon skeleton by one carbon using a nitrile. So we've seen how to add on a nitrile group. So using sodium cyanide, that carbon in your cyanide ion is a new carbon in your carbon chain, right? So here your reactant had 2 carbons, your product has 3. Okay, and of course we can then, hydrolyze that to a carboxylic acid. And of course, there's multiple pathways here. With this alkyl halide, we could have converted that into a Grignard reagent and then tacked on this ethyl group to something with carbon in it. So, for example, if you have carbon dioxide, that will make the corresponding carboxylic acid, as we've seen. Okay, so now when it comes to forming these bonds, it's really important to obviously take into account locants, right? You want to have things in the right places. So keep that in mind. In this example here, we have our carboxylic acid in our product, not on this carbon over here, as you might expect. You don't have that carboxylic acid forming at the benzylic position to make benzoic acid. Instead, you have a carbon in between. We have the carboxylic acid group coming off here. So that alone should tell you that we probably want to insert a carbon here. We're extending the carbon skeleton. Okay, so with that in mind, pause this video and see if you can figure out how to do that. Okay, so if you're back, noticing that we have a a bromide here, an alkyl bromide, I guess, and that we are extending the carbon skeleton. Something that should have popped into your head immediately is making a Grignard reagent. All right, so you do that, and remember, if you have dry ice, that's solid carbon dioxide, you can insert that, or have your Grignard attack that carbon and convert it into a carboxylic acid. And that's actually one way to do that here. Okay, so here we've convert that to a Grignard reagent using magnesium and ether, react that with dry ice, and then you can protonate the resulting carboxylate. Another method that you could have used was to tack on that extra carbon in the form of a nitrile group and then hydrolyze that down to the corresponding carboxylic acid. Okay. Regarding spectroscopy, we have carbonyl. So in IR spectra, this is going to show up typically in that mid 1600s to 1800 range. Depending on the partial single bond character, you would have that signal shifted further upfield. All right. So notice that. As we have, basically when those lone pairs on the groups nearby can help delocalize those electrons and therefore get this to show up, as a single bond. Notice that they are, much further upfield as compared to, an acid chloride here, where that chlorine doesn't have very good overlap with that carbonyl carbon, and therefore those lone pairs don't help as much in terms of making a resonance structure, stabilizing that single bond. Okay. The OH part of a carboxylic acid, I think I've kind of stressed before that that's a really broad peak, taking up about a third of the spectrum. And in the case of a nitrile group, the triple bond between the carbon and the nitrogen shows up somewhere around 2200 wave numbers. For NMR, remember your carbon-13 NMR, the carbonyl carbons will show up around 160 to 185 ppm. The nitrile carbon, so your sp hybridized carbon, is going to show up at around 115 to 130s, right? So that's a way to distinguish between a nitrile versus all of the other acid derivatives. Okay, in terms of a proton NMR, the carboxylic acid proton is attached to an oxygen in that carboxylate group, so it shows up shifted really far downfield at about 12 ppm. Okay, so that's hopefully should be pretty easy to identify. It might be also a bit of a broad peak, because remember that proton's pretty labile, right? So depending on solvent effects, it might be a broad peak, and it might even disappear depending on how well it exchanges with your solvent. All right, let's practice that. So here's a molecule that has a carboxylic acid as well as an ester functional group. Go ahead and predict the carbon-13 spectrum and the proton spectrum. All right, so with the carbon-13, identify the number of signals and figure out their chemical shifts. Just again, roughly where they show up. You can probably get to within 50 ppm or get a range at least for where the signal should show up. In the case of the proton NMR, predict the number of signals, predict roughly where they'll show up, and think about integration and splitting patterns. Okay, so if you'd pause this video and come back now, here are the answers. Okay, so here's the carbon-13 spectrum. So you should have 10 signals overall. And you can kind of just break this down into hybridization. So depending on if you have sp3 versus sp2 versus sp hybridized carbons, they're going to show up further, downfield accordingly. And so carbons 1 and 2 are sp3 hybridized, so they show up in that 0 to 50 ppm range. Looks like specifically a little bit, around the 25 to 50 ppm. Which kind of makes sense, I guess. They're shifted downfield a little bit just due to the proximity to oxygen or a aromatic ring. In the case of carbons 3 through 8, that's part of your aromatic ring, so they show up in that 120 to 150 ppm range. Carbons 9 and 10 are both carbonyl carbons, right? So again, attached to more than carbonyl carbons, they're actually carboxyl carbons, right? They've got a double bond to oxygen and a single bond to oxygen, and they'll show up in that 160 to 200 ppm range. In the case of our proton NMR, we have, you want to look out for multiplicity here, because that'll, if you have equivalent protons, that'll affect your splitting accordingly. In terms of things that can split each other, with proton, the proton over here on your carboxylic acid, that one's really straightforward, right? That's just going to be a broad singlet around like 12 ppm, right? In terms of the other things, it might be better to kind of break this down to groups. Like, so these two protons here are going to split each other and only each other, so they'll both show up as doublets. Okay, they're going to show up in that 7 to 8 ppm range. Well, it looks like it's saying like one of them is going to be a little bit more like 6.5 to 7, but the bottom line is they're going to show up in that range you'd expect for aromatic protons, right? Likewise, hydrogen E over here will also show up in that range. Now that gets split, or actually doesn't get split, because it's kind of isolated. If you look at it to the nearest protons to it, hydrogen A is 1, 2, 3, 4 bonds away. So that's not enough to split hydrogen E. So that also shows up as a singlet. Okay. So then these protons here and here are going to split each other, but they are two sets of 2 equivalent protons. So they split each other into triplets. So that's why we have 2 sets of triplets here. And they're going to show up in that, around 2 ppm. All right, and that's it for this chapter. So let's, go ahead and have a look at some of these practice problems. Okay, so go ahead and name this compound. So again, this one's going to be a little bit more complex than anything you'll see on a quiz or exam. If it helps, remember here we've got 2 carboxylic acid groups, and so they're going to be the terminal groups in your diacid. So we've got 1, 2, 3, 4, 5, 6. So this is hexandioic acid, right? and the rest of these are substituents on that. Okay, so they're a little bit more complicated because they're branch substituents, but that's how you would name that. Okay, the 1,6 is kind of a little redundant. I mean, those carboxylic acids kind of have to be terminal there. Okay, let's go ahead and rank these by pKa values. It might help to think in terms of REO when you're doing this. Okay, so if you're doing that, I'll point out that so A and B are going to be similar, right? They're both carboxylic acids, and you want to look at the difference for C and D, right? For C, you've got a sulfur instead of an oxygen, right? So that's a difference of an atom, the A in REO. Okay, so remember that large squishy sulfur is really good at holding on to a negative charge. So that's probably going to be your most acidic. Over here we have an oxygen, but notice that we have a carbon in between that carbonyl and that oxygen. So this is not a carboxylic acid group. That the negative charge on the conjugate base for this will not be resonance stabilized because that sp3 carbon's in the way. Okay, so this is actually going to be your worst out of all of the of these acids, because while A, B, and D all have oxygen for their protons, or have their protons attached to an oxygen, A and B have resonance stabilization, which D does not. Okay. So the only difference between A and B then, which is going to be in the middle here, are going to be solvent effects. You've got this bulky group over here that's going to prevent solvent coming in and stabilizing the negative charge that the conjugate base here is going to kind of, house. And so this is going to be a worse acid than B. Okay, so if I were to go in order of, increasing pKa values, so that means from low pKa's, which are better acids, to the higher pKa's, which are worse acids, the best acid would be C, followed by B, then A, and then finally D is going to be the worst one. Okay, so let's go ahead and try some synthesis problems now. So here we have alkyl halides, alkyl bromides specifically, and we have various reagents here. Go ahead and pause this video and see if you can figure out the products. Okay, so this first one, you can tell this is going to be a Grignard reaction, right? We're going to use this magnesium to convert this into a Grignard reagent, and then that Grignard reagent is essentially, you've got a carbanion over here. This carbon, that carbanion is attacking the carbon of your carbon dioxide. So it's going to convert into a carboxylic acid there, right? Likewise, over here, we have our cyanide here is going to be our nucleophile, and it's going to replace this bromine. And, so basically we're going to have a cyanide group here, which we then subsequently hydrolyze into a carboxylic acid. So there are your two products. Okay, so, you've, like I said, you've essentially taken that carbon, right, this carbon over here, and added a carboxylic acid group to it. Likewise here, you've swapped out this bromine for a carboxylic acid group. They both do the same thing. You're swapping out a bromine for a carboxylic acid group in multiple steps. All right, here we have an amide. Go ahead and name that. Notice that we have a we have substituent on the nitrogen itself, so don't forget how the locant for that works. And here we have a phenyl ring, and we have substituents on that too. Okay, so here's the answer. It might be easier in terms of nomenclature to treat this as a benzamide group, right? You have a benzene with an amide group coming off of it, so benzamide. And we have methyl groups on our benzene. Okay, so on that benzene, this is the number 1 carbon where our amide group's attached. So we have methyl groups at the 3 and 5 positions. On our nitrogen, we have a methyl group and an ethyl group. So putting that all alphabetically, we have 3,5-dimethyl, N-ethyl, N-methyl. So, the M in dimethyl comes before the N groups here. Okay, and of course within those ethyl comes before methyl, and so that's where the full name comes in. All right. This is again just an explanation question. We kind of talk about this in the lecture. Why are acid chlorides so reactive? You know, so I'm going to kind of gloss over this. Feel free to read this if you like. But again, remember, we tend to focus on more application-based questions. Likewise, here's, again, this is exploring that that same question: why are acid halides so reactive? But from more of a thermodynamic perspective. Okay. All right. So in here, actually, I guess just to summarize those answers really quickly, from a kinetic perspective, you're thinking about how does the reaction happen, right? What affects that transition state, the activation energy for this? So the fact that you want to think about the electronic effects that chlorine has on that carbonyl carbon, making it more prone for a reaction. In the case of thermodynamic perspectives, you want to think about why is this product stable, right? Remember, your chlorine's a really good leaving group, so that also, that kind of helps with the thermodynamics. Okay, with this reaction here, let's go ahead and figure out the reagents we need for this synthesis. So we're starting off with this cyclic acetal, and we wind up with this ester. Okay, so if you pause this and come back, looking at cyclic acetal, you remember you can hydrolyze that pretty easily to a ketone or aldehyde. So just imagine that we hydrolyze this with heat this with dilute acid, and we swap out this, basically this the acetal, right? The oxygens with the connecting carbons here, we swap that out for a carbonyl. Okay, we basically make acetone when we hydrolyze this. Now, if you're trying to look for that in your molecule here, you can kind of see this in two places, right? We've got, this carbon here is a carbonyl. You could see that as the carbonyl. You could see this is the carbon skeleton of your acetone. But you also have to think about, where did this come from? Okay. So I guess the thing here is that the question wants acetone effectively to make both parts of this molecule. Okay, so that's kind of what we're doing here. So in that first step, we're making acetone. In the second step, we need acetone to be the starting point for both halves of our final product. So it might help to kind of work a little retrosynthetically. So, so basically, if you think about this end over here, you think, all right, well, I need some nucleophile to attack that carbonyl, and I must have had some leaving group here. So having an acid chloride makes sense, right? You've got, that chlorine there. This is pretty reactive, so it makes sense that you could then have this alcohol be the nucleophile that makes this ester, right? So going from a ketone to an alcohol is pretty straightforward. You need just a reducing agent like lithium aluminum hydride to do that. Okay, and in 2 steps it goes to that secondary alcohol, and you can't really reduce that any further, right? Over here, we are trying to convert this into an acid chloride, but what's tricky here is the change in carbon skeleton. Notice that we're missing a carbon, right? This carbon over here is gone. So you want to think about reactions that might get rid of that. So for example, if we use a peroxy acid here, peracid like, for the Baeyer-Williger reaction that we learned last chapter, that basically inserts an oxygen and you make the corresponding ester actually, and then you can hydrolyze that into the corresponding carboxylic acid, and then you can convert that into the corresponding acid chloride using thionyl chloride. All right, and so and then once you have those two halves, as I pointed out, this is your nucleophile that attacks that carbonyl, kicks off that chloride, and there's your final ester product. And that's it for this chapter. So Yeah, so again, this is chapter 21. So we just have a quiz after this chapter. After the next chapter, we have an exam. So, be ready to start, brushing up on the previous chapters, go through your old quizzes to start getting ready for that. Okay, and yeah, so do the homework. Try, you've noticed we covered a lot of synthetic problems in this chapter. Again, I'll highlight that, or I'll stress that there are a lot of similarities between the mechanisms. So do try to save yourself some, you know, some of that memorizing capacity there. When it comes to trying to learn these. Though, as I pointed out, if you have the reaction wheel of all the reactions your reagent does and how they're all interconnected, that might be a good thing to put on a flashcard or have in front of you as you're doing your homework or you're studying. All right, but of course, definitely do the homework. Definitely try out, a whole bunch of synthetic problems to try and get the hang of these of these different synthetic pathways.